Welcome to an exploration of the fascinating physics behind Pavlova, where a single material creates two completely different textures. The Pavlova dessert presents us with a remarkable paradox. How does a single whipped egg white mixture create both a crispy shell and a soft marshmallow interior? Let's begin by understanding what egg white actually is at the molecular level. Egg white consists of approximately 90% water and 10% protein molecules. We can express this composition as 90% water plus 10% proteins. Here we see water molecules represented as blue circles and protein chains as interconnected yellow structures floating in the liquid. The primary proteins include ovoalbumin, ovotransferrin, and ovomucoid, each with unique structural properties. When we whip egg whites, we're performing crucial mechanical work on this protein-water system. The whipping action introduces thousands of tiny air bubbles into the egg white liquid. These air bubbles, shown as light circles, become trapped in the liquid phase, with protein molecules beginning to gather at the bubble interfaces. The mechanical stress causes protein molecules to unfold and align themselves at the air-water interfaces. We can represent this transformation as native protein undergoing mechanical stress to become denatured protein. But what actually drives this protein unfolding at the bubble interfaces? The answer lies in surface tension minimization. Proteins reduce the energy cost of creating new air-water interfaces. The surface tension gamma equals force per unit length, approximately 50 millinewtons per meter for pure water. With proteins at the interface, this reduces to approximately 20 millinewtons per meter. Once formed, the foam develops remarkable elastic properties through protein networking. The proteins form a three-dimensional network, shown here as yellow connections between protein nodes, creating a gel-like structure. The proteins stabilize through disulfide bonds between cysteine residues and extensive hydrogen bonding networks. Two thiol groups react to form one disulfide bond plus hydrogen gas. This creates a viscoelastic material with both viscous liquid-like and elastic solid-like properties. The complex modulus G star equals the storage modulus G prime plus I times the loss modulus G double prime. Adding sugar transforms our simple meringue into something capable of the Pavlova paradox. Sugar dramatically increases the viscosity of the water phase surrounding the air bubbles. The solution viscosity equals the base viscosity times e to the power of k times sugar concentration. This graph shows how viscosity increases exponentially with sugar concentration, creating a much more stable foam structure. Equally important, sugar lowers water activity, affecting how water behaves during baking. Water activity equals vapor pressure over pure water vapor pressure, approximately 0.85 in high sugar solutions. During baking, extreme temperature gradients develop across the Pavlova, creating our paradox. The oven operates at temperatures between 120 and 150 degrees Celsius. This temperature gradient visualization shows how heat moves from the red-hot surface through yellow and green zones to the cooler blue core. The heat equation shows temperature change over time equals thermal diffusivity times the Laplacian of temperature. The thermal diffusivity of meringue is approximately 1.4 times 10 to the minus 7 meters squared per second. We express this as alpha approximately equals 1.4 times 10 to minus 7 meters squared per second. At the surface, water rapidly evaporates, creating the characteristic crispy crust. The rate of water evaporation depends on the vapor pressure difference between the surface and the surrounding air. Mass flow rate equals the mass transfer coefficient times area times the difference between saturation pressure and air pressure. Water molecules, shown as blue arrows, continuously escape from the surface layer, leaving behind a concentrated protein-sugar matrix. As water evaporates, the sugar concentration in the surface layer increases dramatically. Surface sugar concentration approaches 80 to 90% by mass. This extreme concentration creates a glass transition, where the material becomes hard and brittle like glass. The glass transition temperature is approximately 60 to 80 degrees Celsius for high sugar meringue. Meanwhile, the interior tells a completely different story of trapped moisture and soft texture. Once the crust forms, it acts as a barrier preventing further water vapor from escaping the interior. The moisture, shown as blue dots, becomes trapped inside the rigid outer shell, unable to escape. The interior temperature remains much lower than the surface due to evaporative cooling from the trapped water. Core temperature remains around 70 to 90 degrees Celsius, well below the surface temperature. The interior retains 15 to 25% water content, compared to less than 5% at the surface. But why doesn't the core also dehydrate completely during baking? The answer is the kinetic barrier created by the crust, which forms faster than heat can penetrate to the core. The trapped water creates internal pressure that contributes to the marshmallow texture. Water at 90 degrees Celsius generates significant steam pressure inside the sealed structure. Steam pressure equals saturation pressure at temperature, approximately 70 kilopascals at 90 degrees Celsius. These red arrows represent the internal pressure pushing outward on the crust from trapped steam. This internal pressure inflates the interior structure, creating larger air pockets and a lighter texture. The crust must be mechanically strong enough to contain this pressure without rupturing. The crust tensile strength must exceed pressure times radius divided by 2 times thickness, based on thin shell theory. Let's quantify exactly how different these two regions are mechanically. The crispy crust has a Young's modulus of approximately 1 to 10 gigapascals. E-crust approximately equals 1 to 10 gigapascals, similar to some plastics. The marshmallow core has a Young's modulus of only 0.121 megapascal. E-core approximately equals 0.1 to 1 megapascal, about 10,000 times softer. This dramatic comparison shows the 10,000-fold difference in stiffness between crust and core. Protein denaturation plays different roles in the two regions. At the surface, proteins undergo complete denaturation and aggregation into a rigid network. Native folded proteins transform into extensively cross-linked, aggregated networks at the hot surface. In the core, proteins undergo only partial denaturation, maintaining flexibility and water-binding capacity. Denaturation rate is proportional to e to the minus activation energy divided by gas constant times temperature. The formation of the Pavlova structure is fundamentally a race between different timescales. The crust forms in approximately 15 to 30 minutes of baking time. T-crust approximately equals 15 to 30 minutes. Water diffusion through the formed crust occurs on a much longer timescale. Diffusion timescales as thickness squared over diffusivity, approximately 2 to 4 hours for a typical crust. This timeline shows how the crust forms much faster than water can diffuse through it, trapping the soft interior. The key to the Pavlova paradox is that the crust forms and seals before the interior has time to fully dehydrate. We can model the Pavlova formation with coupled diffusion reaction equations. Water concentration change over time equals diffusivity times the Laplacian of water concentration minus evaporation rate times water concentration. Protein aggregation density change equals aggregation rate as a function of temperature times protein density times 1 minus protein density over maximum density. These equations are coupled through temperature, which affects both water diffusion and protein aggregation rates. Heat and water transport are intimately coupled with bidirectional feedback between the two processes. Understanding the physics allows us to control the final texture precisely. Higher baking temperature produces a thinner, crispier crust by accelerating surface dehydration. Lower temperature creates a thicker transition zone between crust and core, producing a chewier overall texture. This comparison shows how different temperatures affect the ratio of crust to core thickness. Sugar content affects both the initial viscosity of the foam and the final glass transition temperature of the crust. Glass transition temperature scales approximately as the square root of sugar concentration. Pavlova differs fundamentally from other meringue types in its dual texture. French meringue is baked at lower temperature for longer time, creating uniform crispy texture throughout. Swiss meringue is preheated before whipping, creating uniform, smooth, stable texture ideal for buttercream. Italian meringue uses hot sugar syrup, creating a glossy, dense texture used in toppings. This comparison shows the structural differences between Pavlova and other meringue types. Pavlova is unique in creating two dramatically different textures from a single starting material through controlled gradient processing. Finally, let's address why this paradoxical structure remains stable after cooling. The glassy crust becomes mechanically rigid and impermeable to moisture once cooled below its glass transition temperature. The core remains in a rubbery state because water acts as a plasticizer, lowering its effective glass transition temperature. Glass transition of wet material equals glass transition of dry material minus K times water concentration, where K is the plasticization coefficient. The final structure is a rigid protective shell surrounding a soft deformable core, mechanically stable at room temperature. However, exposure to high humidity can ruin the texture by allowing water to absorb into the crust, softening it. Why does humidity destroy the Pavlova texture so effectively? The answer is that sugar is extremely hygroscopic, meaning it readily absorbs water from the atmosphere. Water absorption is proportional to relative humidity times e to the minus free energy change divided by gas constant times temperature. Let's explore the fracture mechanics that determine when and how the crust breaks. The glassy crust exhibits brittle fracture behavior characteristic of amorphous materials below their glass transition. The fracture toughness KIC equals stress times square root of pi times crack length. There exists a critical crack length above which catastrophic fracture occurs. These stress concentration lines show how cracks propagate through the brittle crust when sufficient force is applied. Critical crack length equals 1 over pi times fracture toughness over stress quantity squared. Let's examine the complete energy balance during Pavlova formation. Energy enters the system through both thermal radiation and convective heat transfer from the oven. Heat input equals Stefan Boltzmann constant times emissivity times area times oven temperature to the fourth minus surface temperature to the fourth plus convective coefficient times area times temperature difference. A large fraction of this energy is consumed by the latent heat of water evaporation. Evaporative heat equals water mass flow rate times latent heat of vaporization. Latent heat of vaporization is approximately 2,260 kilojoules per kilogram.